This unassuming capsule behind me helped NASA chase a question it didn't solve for more than a decade. Can we land a spaceship safely on solid ground? I'm Ewan with the Air Zoo, and this is El Kabong 1, officially designated BT-206. It's a Gemini capsule boilerplate, and it might look like a spaceship, but it wasn't built to go to space. It was built to test how to come home. So first off, what is a boilerplate? A boilerplate is a non-functional spacecraft used for testing and training. Boilerplates often have the same shape, weight, and structure as the real deal, but they often lack complete flight systems. Because of that, they're significantly cheaper to produce. Engineers use boilerplates for drop tests, recovery practice, emergency egress drills, and more. And you can find boilerplates across NASA's human spaceflight programs: Mercury, Gemini, Apollo, the Space Shuttle, and Orion. El Kabong is one of these test articles from the Gemini program, and it let NASA engineers try a bold new idea: land on land. Project Gemini came between Mercury and Apollo. 10 crewed Gemini missions flew between 1965 and 1966, each with 2 astronauts in a capsule built by McDonnell Aircraft. The capsule was, in many ways, an enlarged, more capable follow-on to the Mercury capsule. The program's overarching aim was to develop the skills needed for the Apollo program. Its objectives included carrying out long-duration missions, completing rendezvous and docking with another vehicle, demonstrating extravehicular activities or spacewalks, and to perfect the techniques of atmospheric re-entry and touchdown at a pre-selected location on land. One by one, as the Gemini missions progressed, they completed each of these objectives. Except one: making a controlled land landing. That unsolved objective sets up our story and explains why El Kabong exists. So why even try to land on land? Splashdowns are iconic and practical. The ocean is a vast, mostly obstacle-free landing zone that covers the majority of our planet. But water isn't risk-free. This was learned early on during 1961's Mercury Redstone 4 mission, where astronaut Gus Grissom nearly drowned when the hatch blew early and his capsule began to sink. Water recoveries also consumed major resources. You need ships, aircraft, and personnel. A pre-selected land touchdown could reduce cost and complexity. And remember, NASA's astronauts were some of the world's most skilled and capable pilots. So if anyone could land a space capsule, it'd be them. There was even a morale factor. Some consider land landing a more dignified landing than getting plucked out of the sea looking like a wet rat. So, land landing seemed like a logical next step for our space program, and research began early during the Mercury program and continued into Gemini. But how do you land a capsule like this on land? Engineers envisioned a land landing system with a deployable flexible wing and retractable landing gear. After re-entry, the wing would deploy. The crew would then fly the capsule to the designated site, and the landing gear would absorb the final impact. NASA knew the goal of a land landing was ambitious, and early Gemini missions were still planned to splash down, with the land system phasing in once it was ready. The wing was the key. It had to be responsive, stable, reliable, and compact. And NASA began to develop 2 main concepts: the paraglider, a controllable, flexible Rogallo wing designed by NASA engineer Francis Rogallo and his wife Gertrude, and the parasail, a more parachute-like gliding canopy which had limited maneuvering. On paper, the paraglider looked brilliant. It was lightweight, it packed small for the mission, and then it deployed after re-entry to let the crews glide to the runway. Early small-scale tests of the wing impressed researchers at NASA Langley, and North American Aviation won the contract to develop it further. However, real-world tests proved hard. Inflating and controlling a large flexible wing reliably at the right time, at the right attitude, was complex. Test failures piled up, boilerplates were lost, and delays mounted. By April 1964, after repeated failures, NASA dropped the paraglider from Gemini flight plans and moved the remaining work to flight research. The concept eventually showed promise in later testing, but it was far too late to be included in Gemini. If the paraglider was too complex, maybe there was a simpler compromise between wing and parachute. Enter the parasail, a gliding parachute. It wasn't as maneuverable as the paraglider, but it was simpler and potentially more reliable. It would deploy after atmospheric entry, give limited steering, and use the same landing gear designed for the paraglider program. And because the descent rates were still high, engineers added a pair of retro rockets to fire just before touchdown, shaving off that last bit of speed for a survivable landing. Testing of this concept scaled up quickly, and to run full-scale drops, NASA needed boilerplates. And that's where El Kabong came in. Okay, so let's talk about the name. It's a nod to Hanna-Barbera's Quick Draw McGraw and his guitar-swinging alter ego, El Kabong.
And El Kabong, the righter of wrongs, the champion of justice, the hero of heroes, came to clean up the fair Wild West.
Stick 'em up, train.
Kabong!
As a boilerplate, El Kabong duplicated the size, shape, structural hardpoints, stowage, and mass properties of a spaceflight Gemini. For the parasail program, it also gained additional modifications in order to orientate the capsule correctly for a land landing. Inside, a central Z-axis beam and removable pallets let engineers mount instruments securely near the center of gravity. A pilot view camera could capture approach and landing. The capsule's landing gear was 3 tricycle arranged oleo-pneumatic shock struts with skids to allow a post-touchdown slide. The nose gear was stored in the nose beside a reserve parachute, and the main gear was found in these 2 bays. Between the main gear bays sat the retro rocket bay. This consisted of 2 solid propellant motors chosen for their low weight, compact size, and proven performance in other spacecraft systems. Including retro rockets was a new design to NASA at the time and required altitude sensors. The radar systems of the time were too inconsistent to use, so a physical option was chosen. Early tests tried an in-house pendulum-type microswitch. The space-qualified version, built by de Havilland Canada, used a storable, extendable tubular boom with a force-sensitive tip to trigger the retro rockets right on contact. Put together, the parasail, the gear, the retro rockets, these all formed the Gemini landing system. But the question was, would it all work together? For full-scale testing, El Kabong was carried aloft in a United States Air Force C-119 flying boxcar. An airborne launch cradle ensured a clean release, and a blast deflector protected the aircraft in the unlikely event of an early retro rocket ignition. During testing, El Kabong was dropped at roughly 12,200 feet. The rendezvous and recovery canister would separate. The parasail would deploy and be inflated. The capsule would change its attitude and deploy altitude sensors and its landing gear. Radio commands from the ground would steer the capsule to the landing zone. And when the altitude sensors touched the ground, the retro rockets would fire, slowing the capsule descent, allowing a hypothetical gentle touchdown. Sounds simple, right? Pulling it off end to end proved tough. The first land test suffered a turn motor failure, which caused an awkward landing and the rollover. During the second land test, control lines were cut, plus both altitude sensors malfunctioned, causing an impact too hard for human tolerance. Then, on July 30th, 1965, at Fort Hood in Texas, everything clicked. The system worked as designed. The capsule made a controlled land landing. It was a complete success by test objectives. You know what they say, third time's a charm. But despite this progress, it was too late to implement the system into the Gemini program, and the Gemini missions continued to splash down. The Gemini missions completed all of their original objectives, except for the land landing. In late 1965, NASA gave out contracts to explore using parasails for the Apollo missions, but full-scale results suggested tumbling on the ground, which could cause excessive loads on crews and hardware. Every Apollo mission would splash down. The United States wouldn't achieve routine land landings for a crewed spacecraft until the Space Shuttle era, over 15 years after El Kabong's successful test. El Kabong remained NASA property until 1977. It was then transferred to the Smithsonian Institution and later went on loan to the Michigan Space and Science Center. By 2003, El Kabong was in a rough state, and the Smithsonian loaned it to the Air Zoo, where our world-class restoration team returned it to the condition that you see today. El Kabong reminds us that spaceflight advances not just through the triumphs and successes, but through the almosts and failures. El Kabong is a testament to trying something out, seeing if it works, and learning from the results regardless of success or failure.